Okay, any questions? By the way, I'm kind of going fast. I'm aware of that. But I'm assuming that you are familiar with most of this stuff already, in one form or another form. If you are not, please just ask me. Okay? Any questions? Anything you want repeated? Now, what we had done is basically just, in summary, we had shown that the electric field, we can write it in the form of the gradient of a scalar function, which we will call the electrostatic potential. And then, since it's the gradient of a function, the curl of a gradient of a function is always zero, as long as, of course, you can change the order of differentiation. And for physical systems, we are always allowed to do that. So the curl of the electric field is always zero. Now, the thing that we are trying to head is basically to use what's called the Helmholtz Theorem. What it states is that if you know the curl of a function, of a vector field, and also the divergence of a vector field, plus boundary conditions, then the vector field is uniquely determined. We uniquely know what this vector field is. Well, of course, in a sense, if you just go back to the expression for the electric field, this one, it might be complicated to evaluate, but once we know the charge distribution, we already know the electric field. So there doesn't seem to be any point in doing all these tricks of writing it in terms of the gradient of a function or showing that its curl is zero, its divergence we will be evaluating now. But the problem is we don't always know the charge distribution. For example, we will be looking at cases when we have a point charge in front of a conducting sphere. Well, we already know that that point charge will change the charge distribution of the sphere. So, but the new charge distribution we don't know. We only know that we had put a point charge somewhere nearby. We don't know the charge distribution, so this expression in that case will be kind of useless. But we will see that we know that in front of a conductor, the charge distribution should be such that the surface of the conductor should be an equipotential surface. So that is our boundary condition. We say that on the surface, the potential should be constant. It can be zero, it can be non-zero. We will study both cases. That's our boundary condition. So in that problem, we know the boundary condition, although we don't know the charge. We know that the curl is always zero. Once we determine the divergence of the electric field, although we don't know the charge distribution, we will be able to determine the electric field. And once we determine the electric field, in fact, it will be nice that once we determine the electric field, from that information we can determine the charge density. So that will be basically what we are heading to.
The charge density is just, or distribution is just the divergence. The charge density at any point is just the divergence of it.
Yes, that is what we will show now. Well, although this expression is not always useful in evaluating the electric field, nevertheless it is true. So we can always use it to study the general properties of the electric field. Well, we had seen that this is equal to minus rho of r prime, the gradient with respect to r of 1 over r minus r prime, integrated over the volume. Let's take the divergence of this one with respect to r. Well, the integral is over r prime, and we are taking the divergence with respect to r, so we can just put the derivative inside the integral. Rho of r prime is a function of r prime only, not of r. It's not affected by the derivatives with respect to r. Divergence of the gradient of 1 over r minus r prime. But divergence of the gradient, we had defined it to be the Laplacian. Well, we had studied the Laplacian of 1 over r minus r prime, and it was what was the Laplacian of 1 over r? It was 0 everywhere except when r is equal to r prime. And then we showed that it was, in fact, infinite at r is equal to 0. In this case, it will be r is equal to r prime. So it's a delta function. So in fact, the Laplacian of 1 over r minus r prime was nothing but minus 4 pi, the three-dimensional Dirac delta of r minus r prime. dV. So this is the divergence of the electric field. Just pay attention that sometimes I write this subscript r, sometimes I just drop it. I mean, if there is an ambiguity, then I write it explicitly. If there is no ambiguity with respect to which coordinate we are taking the derivative, I will be dropping it. For example, here I will not drop it because I'll be taking the gradient with respect to r or r prime. That's kind of ambiguous, so I will keep that r over there. But on the left-hand side, the electric field is a function of r only, because we have integrated over r prime. There's no r prime dependence left. So I can just drop it. Now we know the properties of the Dirac delta. You see, if you take the integral of the Dirac delta, the only thing we have to do is just wherever you see an r prime, just put an r. That is what the Dirac delta tells me, since it's multiplied with a function. So it's just rho of r. So this is the divergence of the electric field. Now we also know the divergence of the electric field. Before we already calculated the curl of the electric field, now we have the divergence of the electric field. Now we can also write this in integral form. I mean, in your first year courses we had written this in integral form. What we do is you just take this divergence of the electric field, integrate it over some volume. On one hand, this has to be equal to 4 pi times rho of r integrate over the same volume. But rho times the volume is the charge, but we are just integrating over a finite volume, so this is nothing but 4 pi times the enclosed charge in the surface. We have this volume, we have the Q enclosed is the volume, the charge in this volume. On the other hand, we know the fundamental theorem of calculus. So this is equal to the integral of the electric field over the surface, but which is the boundary of this volume. But this surface, since we have a volume, we are talking about the boundary of this volume as our surface S. It is a closed surface. This should be equal to 4 pi times Q enclosed. So this is the integral form of the Gauss law. So what this states is that if you have any closed surface, then it is bounding some volume inside, then the integral of the electric field over the surface is always equal to 4 pi times the total charge in the surface. This expression and the divergence of electric field expression, the first line, they are equivalent. If you know one of them, you can just derive the other one. So now we have these two equations. We have the divergence of the electric field, we know the curl of the electric field. Given boundary conditions, we can determine what the electric field is. And we will also prove that it is unique.
What about epsilon 0?
Well, you see, if you have, I mean, you missed the first hour. The thing is, let's see, we are using what's called the Gaussian units. Now, in Gaussian units, this constant, the proportionality constant, what we know is we only know that the electric field is proportional to the product of, the force is proportional to the product of the charges, inversely proportional to their distance squared. Well, this observation doesn't tell us which units to use to determine, to quantify the electric charge. In standard units, we are using the Coulomb to specify the electric charge. In terms of Coulomb, this K constant, the proportionality constant, is just 1 over 4 pi epsilon 0. In the units that we will be using this semester, we will be using what's called the Gaussian units. In Gaussian units, that constant of proportionality is 1. So in this unit, the charge, the unit of charge is not Coulomb, but it is the Newton meter squared, everything square root. That's the unit we will be using. And in CGS system, this unit is called the stat Coulomb. So we don't have epsilon 0. I mean, the reason why we will be using these units is that we won't be bothered with epsilon 0. We don't need to keep track of epsilon 0 all around. If we want to go to the system of units with epsilon 0, the only thing we have to do is, instead of the charges we have, every charge we have to multiply with 1 over 4 pi epsilon 0. Then we can just go back and forth between different units. And in these units, we will not have to write this epsilon 0 all the time. So we don't have this epsilon 0 in our Gauss law expression.
We're only working vacuum, right?
For the time being, we are dealing with only vacuum. We will study what happens when there is a medium. So for the time being, we are only dealing with point charges. And conductors, etc. Questions? Well, I'm not going over the exercises where you have calculate the potential corresponding to a uniform charge density of finite length, etc. If you are interested, we can go over them in recitation hours. You will have to do them anyway in your homework. But if you think that something is not clear and you want an example right away, just let me know. So now, what do we know about the electric field? We know that its curl is 0. Now, although we had started by showing that the electric field can be written in terms of the gradient of a function, and hence its curl has to be 0, if you have a function whose curl is 0, that function is always the gradient of a function. And we know that the divergence of the electric field is 4 pi rho. Well, this tells me that the divergence of the gradient of phi is equal to minus 4 pi rho. But divergence of the gradient is what we call the Laplacian of phi is equal to minus 4 pi rho. This is called the Poisson's equation. Laplacian of phi is equal to 0 is what we call the Laplace equation. For example, we will be doing exercises in which we have a sphere, a conducting sphere. The upper portion is kept at a potential plus V0. The lower hemisphere is kept at a constant potential minus V0. What is the electric field? So So we will be solving these problems. Are there any charges around? Yeah, on the sphere, there should be some charges so that they are creating this potential, but out of that sphere, there are no charges. So the electrostatic potential of this problem satisfies the Laplace's equation. With the boundary condition, the surface of the sphere is the boundary of the region where we are trying to evaluate this electrostatic potential, and the boundary condition is that at the top hemisphere phi should be V0, at the lower hemisphere phi should be minus V0. Furthermore, at infinity we are assuming the potential to be 0. So those are our boundaries. So those are the boundaries of the region, where the region outside of the sphere. So we will have to solve Laplace's equation with these boundary conditions. Of course, then you can imagine what if we have some point charge over there, then we will have to solve the Poisson's equation with a Dirac delta density, etc. Now we will do these examples. Once we settle down some of the general properties, we will do some examples. Now let's look at the energy. Energy stored in a charge distribution, or in the electric field. That is what we will be aiming at. So we know that phi is the electrostatic potential. Electric field is equal to minus the gradient of phi. So let's just imagine we have a charge distribution. Q1, Q2, Qi. Now, the energy stored in a given configuration is the amount of work that you have to do in order to bring all the charges to their final configuration. Okay, that is how we define the energy stored. Now, the omega 1. What is the work that you have to do if you want to bring Q1 charge from infinity? That is the first charge. There are no other charges. 0. There is no force acting on it, so you don't need to exert any force on it. It will just eventually come there. So the work done is 0. Omega 2. Well, let's just give some names. The electric field created by the charge Q1, let's just call it E1. The force that this Q2 charge will feel will be Q2 times E1. So Q2 times E1 is the amount of force that is exerted by Q1. So if we want to bring the charge Q2 to its final position, we have to exert the opposite force. This is the opposite force. And the work that we do is nothing but the line integral. This is equal to minus Q2 times, well, we know that the electric field is the gradient of the potential. So let's say it's minus the gradient of phi 1. Phi 1 is the potential created by the charge Q1 only. Dot dl. Well, we are taking the integral of a derivative, which is just the differences at the two endpoints. So it's Q2 times phi 1 at, this is the final point, R2, minus phi 1 at infinity. The potential of a point charge at infinity, we always fix it to be 0. So omega 2 is equal to Q2 times phi 1 at the point R2. Q2 times the electrostatic potential created by the first charge only at the point R2. Well, we can continue like this. The work that we have to do, or the energy stored in the system as we bring the third charge to its final point. This will be Q3 times, well, now the first charge is there, the second charge is there, so the electric field or the force created by the third charge will be due to the electric fields created by the first and the second charge, E1 plus E2. This is the total force that the charges are exerting. If we want to bring this charge from infinity to its final point, we have to exert the opposite charge. And this is the force that we have to exert. And the work done is nothing but the integral of this work over the path. And again, this will be equal to minus Q3 times, we can just write the electric fields as the gradients. This is equal to Q3 times the gradient of phi1 plus phi2 dot dl. And so this is equal to Q3 times phi1 at R3 plus phi2 times R3. Again, I use the fact that at infinity the potentials are zero. And the integral of the gradient is nothing but the differences of the function at the endpoints. Okay, another thing that you have to pay attention to, you see, the integral along a path usually depends on your path. That's, in general, it does depend on the path. But here, since we are talking about the gradient of a function, the integral of the gradient over a path is independent of the path. It only depends on the endpoints. So if you take an arbitrary vector field, if you integrate it over a path, so it's not enough that you specify the endpoints of the path, you have to specify how you go from the initial to the final point, unless that vector field is a gradient. If it is a gradient, the integral will be independent of the path. Whether you start from here, go over such a path, or go over such a more complicated path, the result will only depend at the endpoints. Only if your vector field is a gradient. And in fact, we can just continue like this. If we bring the nth charge, it will be just Qn multiplied by phi I at Rn, where these phi i's are the potentials created by the previous charges at that point. I is equal to 1 to n minus 1. Now we can talk about the total work done. This is nothing but the sum of the works done to bring each charge separately, summed over n. This is equal to sum over n of Qn times sum over I less than n of phi I at Rn. Or let's just rewrite this. I and j and I less than j, Qj phi I Rj. Well, this is the total work done to bring the charges to their final configuration. But it is also the energy stored in our system. So if we just let our system, due to these forces, the charges will just move around, and so we can extract this energy back. In that sense, this is a stored energy, or the potential energy of the configuration. Now we will do one trick. If you consider this sum, there is Q1 times phi 2. No, Q1 times, no, sorry. Q2 times phi 1 plus Q3 times phi 1 plus phi 2 plus Q4 times phi 1 plus phi 2 plus phi 3 Now let's make one observation. Phi I R J. This is the potential created by the charge Qi at the position of Qj. Okay? We said that this was equal to Qi divided by Ri minus Rj. Let us also multiply with Qj. Oh, sorry. Do you agree? But this is equal to Qi times Qj over IR minus, no, Qj times, no, Qi times Qj over Ri minus Rj, which is equal to Qi. Now you see, this is nothing but the potential created at the point Ri created by Qj. Do you agree? So Qj multiplied by the potential created by Qi at the position of Rj is exactly the same as Qi times the potential created by the other charge at that point. Now, I will use that trick to rewrite the above expression. Or let me just use the previous general sum. We had the sum over ij, I is less than j, Qj times phi I of Rj. This is equal to sum over ij, I less than j, Qi phi j Ri, because of this thing we used. Now, let me just change the indices. I'm just renaming indices. Sum over, instead of I will be putting j, instead of j, I will be putting I. J less than I of Qj phi I Rj. I just changed the names. Exchange the names. Well, this is equal to sum over I and j, all possible values, with the condition that I is larger than j, Qj phi I Rj. I just did some aesthetic modifications in how I show that summation. I didn't do anything else. But you see, the total work done is sum over ij, I less than j, or sum over ij, I larger than j. Well, I can add the two terms and divide by 2. Well, if I add the two terms, two summations, and divide by 2, I get the same thing. But when I do that sum, I'm summing over all ij with I is less than j or I is larger than j. So the first term and the second term, they are equal. So if I sum the two, I obtain twice as large a number. So I divide by 2. But now these two summations, I'm summing over all I and j, and the only restriction is that I is different than j. And this is the total work done to bring the system to its final configuration. Well, if I sum over I, what I obtain is nothing but the total electrostatic potential at the position of Rj. There's a single catch though. You see, the potential at the point Rj, its definition, would imply that we are summing over all point charges. But when I am summing over I am summing only over I different than j. So this is one reason why the final results obtained, they will look slightly different. Now we will study what happens, what is the consequence of that in a moment, later on. But just keep in mind that there is this very small difference that we are introducing in this step. In this step, we are kind of removing the restriction that I is different from j. Well, the problem will be, we will see shortly, at least in the discrete case, there's a serious problem because I is equal to j would be the potential created by the charge at its position, which is proportional to the inverse distance from the position of the charge, which is 0. So the term we are kind of adding in the case of discrete charges is infinite. Well, in the case of continuous charges, that term turns out might give a finite contribution. So if you somehow calculate the total work done by different means, you might get slightly different results. But essentially, that's not that important because what we are eventually interested in will be the differences in the energy stored. And the differences of the energy stored will be the same. Because the I is equal to j term is the same everywhere. It is the charge multiplied by the potential created by that charge at its position. No matter how your charges are distributed, it's the same number, either the infinite or finite, same constant. So when you look at the differences or the changes in the potential energy stored in the system, which is the only physical quantity, there is no difference. Okay, so let's continue. I can write this as an integral also. We can just, instead of just summing over the discrete charges, we can convert it into an integral. And in the integral form, the total work will be 1 over 2 rho of r, the potential at the point r, dV. Well, next day, I will pick up from here. But just to give you an idea of where we are heading to after this step, that I will just go over it fast. If you are not following, I will just pick up from here. But what we can do now is, this is 1 over 2. We know what the density is in terms of the electric field. It is just the electrostatic potential. So I can write the charge density in terms of the electrostatic potential as minus 1 over 4 pi Laplacian of phi multiplied by phi dV. This is equal to minus 1 over 8 pi. Let me write it, the divergence of phi times the gradient of phi minus the divergence gradient of phi, that gradient of phi. Well, I'm basically using the chain rule. If you take the derivative of this term, you get the divergence of the first one multiplied by the divergence of the second one, which will be cancelled by this one. And you will get the first one multiplied by the divergence of the second one, which is the Laplacian of phi. But in this form, the first term I can just, it's the divergence of a vector field integrated over a volume. It becomes a surface integral. Plus 1 over 8 pi. Well, the gradient of phi is the electric field minus the electric field. I have two of them. So if you take it, just becomes the electric field squared dV. Well, if you imagine the surface to be at infinity, the potential is 0 there. So the first term is 0. So the total work done is equal to 1 over 8 pi times E squared dV. Or the energy density stored in the electric field is equal to 1 over 8 pi times E squared. Well, if you remember, we had derived this relation, you had also derived this relation in your general physics course for a parallel plate capacitor. If you start from a parallel plate capacitor, ignore the fringing effects, then you can obtain the energy stored in an electric field, the energy density stored in the electric field. It has exactly the same expression. But this result is not restricted to a parallel plate capacitor. This is an exact result. Although in that derivation you ignore the fringing effects, this is an exact result. There is an energy density stored in the electric field which is proportional to the electric field squared. Now this is kind of the first time that the within this second week, that the electric field itself has its own physical properties. We first defined the electric field just as a mathematical trick to convert everything to local expression in the first hour. Now we see that the electric field itself has some physical properties like the energy. The electric field itself has energy, not the charges. And throughout the lecture, we will also see that the electric and magnetic fields, they also have momentum. Just like an ordinary particle, they have energy, they have momentum. So we say that the electric field itself, although for the time being it's just a mathematical trick, mathematical definition we made, we will say that the electric field itself has its own physical existence. I will repeat this in the next hour that we will have. No, any questions before you go? Well, for the time being, we are looking in electrostatics. Only electrostatics, no moving charges. But towards the end of the semester, what we will study is we will study the electric and magnetic fields created by a charge that is moving at some arbitrary speed. It can be as close as you want to the speed of light. So we will see what kind of an electric field it creates. Okay, so see you on Friday.